A rider dressed head to toe in an Imperial Scout Trooper costume.
Right, from Star Wars.
Exactly. And they were flying through this incredibly dense forest. But the vehicle they were on, I mean, it had no wheels, no wings, no visible propellers anywhere.
It's just a sleek carbon fiber frame.
Yeah, just hovering a few feet above the dirt, banking through these trees at a really high speed. It looked exactly like a speeder bike from Return of the Jedi.
Which naturally made half the internet immediately scream that it was fake.
Oh, the comments were just a mess. Everyone was labeling it a visual effects project, pointing out, supposed rendering errors. People were convinced it was AI generated.
It's funny because our brains are just so conditioned to look for specific visual cues when something flies.
Right, like rotors or wings.
Exactly. If you see a helicopter, your brain registers the massive spinning rotor and, subconsciously accepts that it creates lift.
Mix.
And with an airplane, you see the wingspan and you understand gliding.
Hmm.
But when you take those physical structures away and hide the propulsion system, in this case, microjet turbines tucked right inside the chassis, it causes this total cognitive dissonance.
It just looks wrong to us, like the physics are broken.
Right. The visual input doesn't match our understanding of fluid dynamics. So our first instinct is just, oh, it's digital manipulation.
Well, and I'll admit, as a journalist who covers emerging transport tech all the time, my first instinct was totally to agree with the skeptics.
You thought it was fake, too.
I really did. I actually pulled the video into my editing software, looking for masking artifacts around the edges or, weird lighting where a physical rig might have been painted out.
But you didn't find any.
No. And after spending hours digging through official technical specs from the manufacturer, plus these really deep dive architectural analyses from Opta's architecture and reports from New Atlas and Futurism, I'm here to tell you, the machine is 100% real.
It really is.
Yeah.
And it runs on actual jet fuel.
Which brings us to the mission for today. Welcome to the deep dive. Today we are completely unpacking this machine, which is called the Volonaut Airbike.
We're going to look at the mechanics of microjet propulsion and figure out the digital flight stabilization needed to keep this thing from just flipping over.
Right. And we also have to dig into these really specific, kind of archaic FAA regulations to see if you could ever actually use this thing for a morning commute.
Because the marketing really pushes that commuter angle.
They do. And we've got a huge stack of sources to work through, including YouTube reviews from Tinker, interviews with the inventor himself, and all that FAA Part 103 regulatory stuff.
It's a lot to cover.
It is. And, as a journalist, I love the tech, but as a parent of two, I am constantly looking at the practical reality of these machines. Like, if this is personal air mobility, I have to ask the hard questions.
Like safety questions.
Exactly. Thermal exhaust, noise. What happens if an engine just dies when you're 15 feet in the air? Would I ever let my kids anywhere near this thing?
Probably not after we get through the thermal specs. But to really understand why the Airbike is built this way, we have to look at the guy who designed it.
Right, Tomasz Patan.
Yeah, he's a Polish inventor and engineer. And his background is super interesting because he didn't come from, Boeing or Lockheed Martin.
He wasn't doing traditional aerospace engineering.
No, not at all. Those massive companies do years of theoretical modeling before they even machine a single part. Patan came from aerial photography and heavy lift drones.
Oh, wow. Okay, so he was building custom drone rigs.
Exactly. For over a decade, he ran an aerial film company. So he was constantly having to build these custom multi-rotor systems to carry bigger and heavier cinema cameras.
Which leads right into that Tinker interview I was reading. Patan talked about how dealing with those heavy cameras basically forced him into manned flight.
Right, because of the cube-square law.
Yeah, exactly. He said that as the camera payloads got heavier, he had to increase the size of the electric rotors. But when you double the size of a rotor, you increase its area by 4.
And the weight of the batteries and the supports scales cubically. It gets really heavy really fast.
Right. So he hit this threshold where his custom drones could lift like 80 to 90 kilograms. And he basically looked at the math and went, wait a minute, I could just put a person on this.
Just swap out the camera gimbal for a seat.
Yeah. And that realization led to his first huge success, right? The Jetson 1.
Yeah, the Jetson 1. It was an EVTOL, so an electric vertical takeoff and landing vehicle.
And it looked completely different from the Airbike.
Totally. It had 8 big electric rotors spread out across this really light aluminum and carbon fiber frame. And because it was all electric, there were 0 local emissions.
And electric motors are pretty mechanically simple, right?
Oh yeah, one moving part. Plus they give you instant torque. That makes it so much easier for the flight computer to stabilize the vehicle because it could just tweak the RPM of the individual rotors in like milliseconds.
That makes sense. I saw it cost around $128,000, and you got about a 20-minute flight time. People were calling it the Tesla of the skies.
And his development process for it was insane. He basically lived in his office with a bunch of high-end 3D printers.
Just constantly prototyping.
Yeah, he would print a structural part, stress test it until it snapped, look at why it broke, tweak the computer model, and then immediately print the next one.
That agile development is how he got it to market so fast. But okay, this is where I get a bit stuck, and this is the core tension we need to talk about.
The pivot to jets.
Yes. The whole transportation industry is aggressively moving toward electric, right?
Absolutely.
And the Jetson one was successful, it was clean, it was relatively quiet. So why would this guy totally abandon that successful electric platform and build the Volonaut Airbike, which literally burns highly volatile jet fuel?
Well, it all comes down to aerodynamic drag and where you actually want to fly the thing.
Okay, unpack that for me.
So electric multi-rotors are great for stable hovering, but they are terrible if you want to fly fast or get into tight spaces.
Where are the batteries?
Partially. To lift a 200-pound person with electric power, you need massive lithium-ion batteries. And batteries have awful energy density compared to liquid fuel.
Right, they're just so heavy.
Super heavy. And to lift that heavy battery, you need huge rotors with a really wide diameter. So the Jetson 1 was like 8 feet wide with these spinning blades sticking out.
Oh, I see. So if you're trying to recreate that Star Wars forest chase.
You can't. An 8-foot-wide vehicle with exposed propellers in a dense forest is a death trap. If you clip one branch, the carbon fiber blade shatters.
And you immediately lose lift on one side and crash.
Exactly. You get asymmetric lift and you are going down hard.
Wow. So the physical size of an electric hoverbike totally dictates where it can go. If you want it to feel like a nimble dirt bike, you have to ditch the big rotors.
You have to. But of course, if you ditch the rotors, you lose your lift.
Right. So you need a propulsion system that has a way higher energy density and a massive thrust-to-weight ratio, which is where the microjets come in.
Exactly. And the weight difference is staggering.
Hmm.
The dry weight of the Airbike, so without fuel, is only 30 kilograms. That's about 66 pounds.
That is insane. Just for context, a regular street motorcycle like a Honda CBR or something weighs like 400 pounds.
Right. And a motorcycle only has to push itself forward on flat asphalt.
Yeah. The Airbike is 7 times lighter than a normal motorcycle, and it has to fight gravity to lift a human. How did they even get it that light?
Extreme reliance on advanced metallurgy and aerospace-grade carbon fiber. But the real magic is in those microturbines.
I know Volonaut has been kind of secretive about the exact engines they use.
They have.
Mm-hmm.
But the tech analysts at New Atlas cross-referenced the visual data and the fuel consumption numbers.
What did they find?
They're pretty sure it uses a cluster of engines that are basically similar to the JetCat P400 Pro, or maybe a custom version they built in-house.
And these are tiny, right? Like the size of a fire extinguisher.
Yeah, exactly. But they work on the exact same thermodynamic principles as a giant turbofan on a Boeing 747.
The Brayton cycle.
You got it.
Okay, let's break down the Brayton cycle for the listener because it's fascinating. It's constant pressure combustion, right?
Right. So first, the engine draws in ambient air.
Using a compressor.
Yeah, centrifugal compressor. It pulls the air in, squeezes it down, and then pushes it into an annular combustion chamber.
And that's where the fuel comes in.
Exactly. Atomized fuel is injected into that compressed air and ignited. The gases expand violently, and they get forced out the back.
But before they shoot out the back, they hit another turbine, right?
Yes. That rear turbine is connected by a central shaft all the way back to the front compressor.
So the exhaust is actually powering the intake of more air.
It's a continuous loop.
Yeah.
And whatever energy is left in the exhaust gas after it spins that rear turbine, that's your raw thrust.
And these things are spinning incredibly fast.
Over 100,000 RPMs, which is why they make so much thrust for their size. It let them ditch the massive batteries in electric motors.
Okay. But as I was reading the OPTES architecture analysis, they pointed out a massive problem with doing this. When you use a big propeller, you're pushing a huge column of air pretty slowly.
Right, it's a wide distribution of pressure.
But with these microturbines, you're pushing a tiny amount of air at supersonic speeds. OPTES called it the thrust print.
It's essentially 4 violent, highly concentrated pillars of fire.
Yeah. Like strapping 4 industrial leaf blowers to a carbon fiber bar stool. The heat must be unbelievable.
Oh, the exhaust gases coming out of those microturbines can easily hit 700 degrees Celsius.
That is just terrifying. As a parent, I'm just picturing a kid running up to this thing in the driveway. It's a mobile furnace.
It really is, and it creates this intense dynamic pressure on the ground when you hover. It's called the ground effect.
What happens when it hits the ground?
Well, the high-velocity exhaust slams into the dirt or asphalt, spreads out horizontally, but then a lot of it recirculates right back up.
Oh, so it bounces back into the engines.
Yes, and that creates a massive risk called hot gas ingestion, or HGI.
Let me guess. Engines don't like breathing their own superheated exhaust.
They hate it. It's oxygen depleted and very hot, which completely changes the air density entering the compressor.
Which causes what?
A compressor stall. Basically, the engine chokes, and you lose all thrust instantly.
Okay, and that brings me to the fail-safe mechanisms. Because to me, this is the biggest issue with vertical takeoff. If you're flying a Cessna and the engine quits, you still have wings.
Right, you pitch down and it becomes a glider. You have time to find a field.
But the Airbike has the aerodynamic profile of a brick. If you lose thrust at 15 feet, you just fall, gravity wins instantly.
You can't even auto-rotate like a helicopter because there are no big rotors to store that kinetic energy.
So what happens if an engine flames out?
This is where Patan really had to level up his engineering from his drone days. The Airbike uses a triple redundant turbine system.
So it's not just the pilot manually controlling 4 engines.
Not at all. The engines are all networked together on a high-speed data bus, feeding right into the flight controller.
Monitoring the heat and RPMs.
Exactly. Exhaust gas temperature and shaft RPM. If an engine ingests a bird, or just mechanically fails, the system knows in milliseconds.
And what does it do?
It instantly changes the thrust vectoring and throttles up the remaining healthy engines to balance out the lost lift.
But wait, didn't we just say earlier that jet engines have lag? Like electric motors have instant torque, but jets have to spool up the compressors.
They do. There's a delay.
So if an engine dies, how does the computer stop the bike from just instantly rolling over while it waits for the other engines to spool up?
That is arguably the hardest control theory problem on the whole machine. To deal with the lag, they probably run the engines at a higher baseline RPM than they actually need to hover.
Oh, so they have extra power already spooled up and they just vent the excess thrust away?
Yes. Or the flight computer anticipates the lag and uses internal servos to physically tilt the healthy engines. It aggressively vectors the thrust to hold the chassis level while they spool up.
Just to keep you upright.
Right. If an engine dies, the computer's only priority is arresting the roll, stopping the momentum, and starting an automated controlled descent. It just wants to put you on the ground safely.
The physical stress that must put on the frame is wild. When the computer suddenly yanks those thrust vectors around, the torque on a 66-pound frame must be extreme.
It is, and that's why they use 3D printed metal parts for the engine nodes.
I saw that in the specs. Direct metal laser sintering.
Yeah. Instead of just standard aluminum tubes, they use software to generate these organic, skeletal-looking lattice structures.
Just putting titanium exactly where the stress loads are highest?
Exactly, down to the millimeter, while hollowing out the parts that don't take any load to keep that weight down.
It's brilliant. But honestly, all that structural strength doesn't matter if the human interface is a mess.
Which is a huge challenge. A hover bike is inherently statically unstable.
Yeah, it's like trying to balance a broomstick on the palm of your hand.
Exactly. A human being simply cannot process sensory information fast enough to manually balance 4 independent jet turbines.
If they gave you 4 manual throttles, you'd crash in 2 seconds.
Without a doubt.
Which means we need to talk about the brain of the bike, the digital flight stabilization. They call it a fly-by-wire system, but I really want to break down what that actually means here.
Well, traditionally, fly-by-wire just means there are no physical cables between the pilot and the engines.
Right, you aren't pulling a steel cable that mechanically opens a fuel valve.
No. You make an input, the flight computer reads it, and the computer decides how much thrust to actually give the engines.
And the core of that system is the PID controller, right?
Yes, a proportional integral derivative controller, and it works constantly with the IMU, the inertial measurement unit.
Okay, so the IMU is the sensor packet.
Right. It's got highly sensitive gyroscopes to measure rotation, accelerometers to measure linear movement, and magnetometers for magnetic heading.
So it knows exactly what the bike is doing in 3D space.
Thousands of times a second.
But here's the catch I was thinking about. Those 4 microturbines are spinning at over 100,000 RPM. The vibration must be horrific.
It creates massive high-frequency harmonic resonance right through the carbon fiber.
So if all that vibration reaches the IMU, wouldn't the gyroscopes just output total garbage data? Like, the computer would think the bike is violently shaking when it's just hovering.
That is a huge problem. So they have to isolate the IMU physically with mechanical dampeners.
Like rubber mounts.
Yeah, specialized mounts. But they also use advanced software filtering, typically Kalman filters.
What do those do?
Mathematically, a Kalman filter looks at the raw data and strips away the high-frequency engine vibration noise, leaving only the actual low-frequency movement of the vehicle.
Oh, that's clever. So the computer gets a clean picture of the bike's attitude, and then it can issue those tiny thrust micro-adjustments to keep it level.
Precisely.
Yeah.
But Volonaut took the control scheme even further. You don't just steer this with a joystick.
Right. This is the coolest part. You wear a telemetry-based helmet.
Yeah, the helmet itself is an interface. It feeds data straight into the onboard computer.
And you steer mostly with your body weight, like riding a jet ski or a dirt bike, right?
Mostly, yes. It's a sensor fusion algorithm. The helmet tracks where your head is and where you're looking.
Wow.
And there are strain gauges in the foot pegs and the handlebars to measure exactly where your mass is distributed.
So if I lean forward,
The sensors feel your center of gravity shift. The computer takes that as a command to go forward. So it imperceptibly drops the thrust on the front engines, increases thrust on the back engines.
a nose dips down and you get pushed forward.
Exactly. And the pilot reviews talk about how incredible this feels.
I read some of those. Because there's no cockpit, no glass in front of you.
You get a completely unobstructed 360-degree view.
And you don't feel like you're fighting the machine because the computer's doing all the stressful math to keep you from crashing.
It creates this illusion that the machine is just a biological extension of your own body.
Yeah.
You lean,
Yeah.
and you just glide.
Plus, the computer handles all the scary stuff. Auto takeoff, auto landing.
Yeah, there's a radar altimeter on the bottom that measures the exact distance to the ground, so it lands perfectly soft every time.
And if you get vertigo while dodging trees at 100 miles an hour.
You literally just let go. Return your body to a neutral posture, and the computer slams the brakes on, levels out, and goes into a GPS-locked hover.
That level of automation is what makes the marketing pitch sound so plausible. Because Patan keeps talking about this commuter dream.
Right, turning a 15-minute traffic jam into a 4-minute flight to the office.
And as a journalist who covers urban infrastructure, I hear this all the time.
Hmm.
Every VTL startup promises to fix traffic.
It's the standard pitch.
So let's actually test this. Let's compare the theoretical airbike commute to the current king of urban commuting, the motorcycle.
Okay, well, mathematically, the airbike wins, hands down.
Because it ignores traffic.
Exactly. A motorcycle is great because you can lane split. You bypass all the stationary cars.
But you're still stuck on the 2D plane of the road.
You still have to deal with potholes, red lights, and the biggest danger.
Someone opening their car door right into you.
Yes. The airbike ignores all of that. You move in 3 dimensions, point to point, right over the obstacles.
And the speed. The specs say it can hit 124 miles per hour. That's 200 kilometers an hour.
Faster than highway traffic.
But okay, let's bring in the reality check here. Introducing a jet vehicle into a city creates massive environmental and physical chaos.
Oh, the externalities are huge. The marketing completely ignores the thrust print we talked about earlier.
Let's talk about that. If I take my normal motorcycle to get coffee, I roll up, deploy the kickstand, and walk inside.
It's a non-event.
But if I fly my airbike to Starbucks, I'm coming down with 4 supersonic columns of 700-degree exhaust.
You would destroy the parking lot. The radiant heat from hovering would soften the asphalt binder almost instantly.
And if there's any loose gravel or dirt,
The thrust weaponizes it. You would essentially create a localized hurricane that sandblasts every car within 50 feet.
shattering windshields, pelting pedestrians with rocks.
It would be chaos. And what if you try to land on the grass next to the coffee shop?
The exhaust starts a brush fire.
Instantly. The thermal output is a massive fire hazard.
And then there's the noise. I mean, the whole reason the Jetson 1 was electric was to keep it somewhat quiet.
Right. Electric multi-rotors make a low-frequency hum. It's loud, like a big drone, but you can tolerate it.
But jet engines make that high-pitched tearing scream.
The shearing effect of the hot exhaust mixing with cold air creates acoustic energy that actually hurts your ears up close.
It pierces right through residential walls. You'd wake up the entire neighborhood. Every dog would be barking, car alarms going off.
It is incredibly antisocial to fly a jet in a populated area.
Which is exactly why the government is so strict about this stuff. And this brings us to the legal puzzle. Volonaut heavily advertises that you don't need a pilot's license to fly the airbike.
Which sounds completely illegal to most people.
Right. The FAA controls all the airspace in the U.S. How is an untrained civilian legally allowed to fly a jet?
It all comes down to a really specific loophole from 1982, AFAR Part 103.
The ultralight regulations, I went down such a rabbit hole reading about this.
It's a fascinating piece of law. Back in the early 80s, people started strapping two-stroke lawnmower engines to canvas hang gliders.
And the FAA was just looking at this like, what do we do?
Exactly. They didn't want the bureaucratic nightmare of registering thousands of dangerous kites, and they didn't want to force hobbyists to get medical exams.
So they basically created a carve-out.
Part 103. It says that if your vehicle meets some incredibly strict rules, the FAA refuses to even call it an aircraft.
They designate it an ultralight vehicle.
Right. And because it's an ultralight, it doesn't need an airworthiness certificate. It doesn't need a tail number.
And you don't need a license or any training whatsoever. You could buy an air bike, unbox it, and fly it that afternoon.
Theoretically, yes. But those restrictions are brutal.
Let's go through them. First, it has to be single occupancy only.
Just one seat.
Second, it can only be used for recreation. You can't use it for commercial gain, so no air bike Uber service.
Definitely not.
And third, the weight limit. If it's powered, the empty weight cannot exceed 254 pounds.
And the airbike is only 66 pounds, so it passes that easily. The FAA made that rule so that if you crash an ultralight into a house, it doesn't have enough kinetic energy to bring the house down.
That makes sense. But the fourth rule is the kicker. You are legally allowed to carry a maximum of 5 U.S. gallons of fuel.
Which totally kills the utility. 5 gallons of Jet A1 fuel weighs about 34 pounds.
Even if the frame could hold a 20-gallon tank easily.
They can't do it. The second you add a 6th gallon, the FAA reclassifies it as an experimental aircraft, and you suddenly need a pilot's license.
So that's why the flight time is so short.
Exactly. And the final rule is the speed limit. Under Part 103, your top speed in level flight cannot go over 55 knots.
Which is about 63 miles per hour. But wait, the Volonaut specs say it can do 124 miles per hour? How do they get away with that?
They use an artificial software governor.
Oh, they electronically cap the speed.
Right. The flight computer physically limits the forward thrust vector so you can't break 55 knots.
And the FAA accepts that.
As long as the manufacturer approves, the pilot can't just flip a switch and bypass it mid-flight, yes.
Okay, so let's summarize the commuter dream. We have a single-seat bike, artificially speed capped to 63 miles per hour with 5 gallons of gas, but no license required.
Right.
So I can still legally fly it to work, right?
Absolutely not. And this is the fatal flaw for the whole flying commute pitch.
The congested area rule.
Yes. Regulation 103.15 strictly bans operating an ultralight over any congested area of a city, town, or settlement, or over any open-air assembly of persons.
And in aviation law, congested is terrifyingly vague. Does that mean downtown Manhattan, or does it mean my cul-de-sac?
The FAA refuses to give a strict geographical definition. They decide on a case-by-case basis when they find people.
I read aviation lawyer Rick Durden's analysis of this. The precedents are wild.
The NTSB judges almost always side with the FAA's broadest, strictest definitions.
Right. Like, they've ruled that a tiny suburban subdivision with less than 20 houses is technically a congested area.
They've also ruled that a stretch of interstate highway with moving traffic is congested. You can't even fly over the highway.
Durden even found a case where a handful of people standing on an empty airport tarmac was legally ruled an open-air assembly of persons.
So if you fly over 3 kids playing soccer in a park, you're breaking federal law.
That completely destroys the commuter use case. You can't fly over your neighborhood. You can't follow the highway.
Plus, Part 103 is daylight only. No flying at night, no flying in clouds. You need total visual clearance.
And if you break the rules today, everyone has a smartphone. A 120 decibel jet screaming over a suburb is going to get filmed by 50 different people.
The FAA will see the video, subpoena the GPS logs right out of your helmet, and ground the vehicle immediately.
So it's legally useless as transportation. You have to fly it over empty fields or massive private ranches.
It's purely a recreational toy.
Which brings me to the $880,000 question. What is the true cost of this thing? Both for your wallet and for the planet.
Well, financially, it's astronomical. The Tinker Review confirmed it retails for $880,000, and you have to put down an $80,000 non-refundable deposit just to get on the wait list.
That is just offensive money for a toy. Let me give you some perspective. For $450,000, which is roughly half the price, you can buy a brand new factory-certified Cessna 172.
A real airplane.
Yes, an enclosed 4-seat aircraft. You get cabin heat, advanced avionics, you can fly through the clouds on
And you can
instruments,
carry 4 adults.
and fly for 4 hours straight. The Airbike costs twice as much, carries one person, and because of the 5-gallon fuel limit and the thirsty jet engines, you get a maximum of 10 minutes of flight time.
It's an engineering trophy. It's paying double for 1/12 the utility.
You take off, zoom around an empty field for 6 minutes, and then you have to land before you fall out of the sky.
It's a technological flex for eccentric billionaires and venture capitalists.
But the environmental cost is what really bugs me, because Patan's last vehicle, the Jetson 1, was all about clean electric aviation.
Right. No local emissions.
But the Airbike is a massive step backwards. We are burning highly refined jet fuel just to move a single human around for 10 minutes.
The thermal inefficiency is brutal. Using microjets for vertical lift requires so much energy compared to a commercial airliner wing.
It just feels irresponsible burning that much fuel for a 10-minute adrenaline rush.
To be fair, Volonaut says the turbines can run on biodiesel.
Does that really solve anything, though?
It's a band-aid. Biodiesel reduces the net new carbon in the atmosphere, sure, because the plants it's made from absorbed carbon recently.
But it's still combustion.
Exactly. You are still dumping intense heat, acoustic pollution, and particulate exhaust into the air. It might be slightly a greener fuel, but it's still fundamentally inefficient.
So we've spent this whole deep dive unpacking a machine that totally breaks our expectations of flight. Tomasz Patan took 4 jet turbines, an incredibly complex fly-by-wire computer, and crammed it into a 66-pound frame.
It's a genuine marvel of modern material science.
It really is. It exploits this quirky 1980s legal loophole to let you fly a jet without a license and gives you this pure sensory flying experience.
But the brutal realities of fluid dynamics, noise, and FAA rules ensure it'll never actually replace your Honda Civic.
It's an $880,000 toy. It's the ultimate collision between sci-fi dreams and messy, real-world physics.
And it makes you wonder how the government will handle this stuff when the tech actually gets cheaper.
Which actually leads me to a final thought for everyone listening to chew on. Right now, this thing is loud, it's expensive, and it's relegated to private ranches.
For now.
But tech evolves. What happens in 30 years if engineers figure out acoustic dampening? What if they make jet bikes truly silent?
And cheap enough for the middle class.
Exactly. And the AI is so good you can't crash. If our cities suddenly fill with thousands of commuters flying at 60 miles an hour, point to point, totally ignoring the roads, who actually owns the airspace 10 feet above your driveway?
That's a scary thought.
Are we going to have to buy the air rights to our own front yards just to stop flying commuters from cutting through our trees to beat traffic?
It's going to be a legal nightmare.
It really is. Something to think about the next time you hear a strange noise in the sky.